Welcome to AI Tech Pathways. In today's explainer, we are doing a comprehensive overview of Lecture 17 from Stanford's highly acclaimed course on deep reinforcement learning. We're going to explore a really fascinating shift happening in the industry right now. We'll look at how reinforcement learning, or RL, is pulling artificial intelligence out of those perfectly ordered digital simulations and literally thrusting it headfirst into the chaotic, messy physical world we live in. We are talking about completely blind robots walking over squishy mattresses, tiny robots conquering giant human-sized stairs, and AI learning to physically feel the environment around it. It's an absolutely thrilling journey, so let's just get right into it.
So, here is our roadmap for today. We'll start with the 2 pathways of AI learning, followed by the recipe for RL success. Then we'll tackle the sim-to-real gap, giving robots direct vision, and grasping the physical world. And finally, we will wrap things up by looking at exceeding human capabilities. We're basically going to start with the fundamental software concepts and then progressively move toward the really wild, real-world physical challenges of advanced robotics.
Section 1. 2 pathways of AI learning. Let's kick this off by defining the 2 massive training paths that essentially dictate how an AI actually learns to interact with the world around it.
Now, to truly appreciate what makes modern robotics so mind-blowing, we really have to contrast imitation learning with reinforcement learning. So imitation learning is widely used to pre-train vision language models. It relies on off-policy data, which essentially means data generated by humans. And, it's great at taking a clean data set to build generalist models that can do a variety of tasks decently well just by mimicking us. But reinforcement learning, well, that's a completely different beast. RL is on policy. It learns through relentless trial and error, generating its own data. And what makes it so incredibly powerful is that absolutely every single data point is fair game. It learns from its successes, sure, but critically, it learns from its failures, its negative data. This endless cycle of trial and error is exactly what creates incredibly precise superhuman specialists. I mean, think of the famous AlphaGo system that utterly defeated world champions.
Section 2. The recipe for RL success. Now that we've identified RL as the ultimate pathway to superhuman precision, let's look at the absolute must-haves for this approach to actually work in practice. The crucial takeaway here is that RL basically relies on 2 foundational ingredients. First, you absolutely need well-specified rewards. Think of that game of Go again. The win and loss rules are crystal clear. You can programmatically, mathematically define success. Second, you need the ability to run these policies at a massive scale. Because we can build perfect digital simulations of games like Go, we can simply throw mountains of computing power at the problem, efficiently converting that compute directly into training data. If you have clear, automated rewards and scalable simulation, RL works like absolute magic.
Section 3. The sim-to-real gap. Now here is the massive catch when it comes to robotics. Moving these heavily trained policies from perfect digital simulations into the completely unpredictable physical world introduces our biggest villain of the day, the sim-to-real gap. You might be wondering, how exactly do you train a robot in a simulation and then just drop it into a real-world living room without it immediately falling over? The breakthrough here is rapid motor adaptation, or RMA. When deployed in the real world, the robot literally doesn't know the friction of the floor or the exact mass it's carrying. So it uses a module running at 10 Hz, 10 times a second, that constantly looks at the robot's proprioceptive history. Basically, it compares the movement the robot's brain commanded to the movement that actually happened. If it commands a step forward but the leg slips further than expected, the RMA module instantly deduces, oh, okay, the floor is slippery, and it adjusts its physical mechanics in fractions of a second. It is quite literally feeling its way through the world.
And this brilliantly illustrates the sheer power of RMA. In the Stanford lecture, they showed these incredible real-world tests where a single policy was deployed 0 shot. That means absolutely no fine-tuning for these specific environments. It just worked out of the box. A blind quadruped robot successfully walked over a squishy, unpredictable mattress. It kept its balance while walking on a plastic tarp covered in literal olive oil. They even dropped a 5-kilogram payload onto a 12-kilogram robot while it was actively walking. The robot practically buckled, but the RMA module instantly detected the anomaly, shoved more torque into the motors, and totally recovered its gait. It's unreal.
Now look at the comparison we're highlighting here. Pay attention to the system ID method. This is the old school approach where engineers try to explicitly force the AI to guess exact mathematical parameters, like the literal coefficient of friction or the exact mass of an object. And guess what? It actually has the lowest success rate. Trying to explicitly calculate precise real-world physics on the fly is just way too hard and too noisy. RMA wins because it doesn't actually care about the exact math. Instead, it creates a compressed, rapid understanding of its environment in real time, which results in the highest success rate and incredibly smooth motor control.
Section 4. Giving robots direct vision. Up to this point in the explainer, these incredible feats of physical recovery have been completely, 100% blind. But if we want truly general-purpose robots, we have to upgrade their senses.
Which naturally leads to a fascinating, maybe even provocative question. If blind adaptation works so incredibly well, flawlessly recovering from oil slicks and sudden dropped weights, do robots even need vision to walk? It's a great question, but the reality is, while blind walking is fantastic for sheer robustness, vision is fundamentally required for two big things: identifying gaps you literally have to jump over and operating elegantly. If a robot just blunders into a staircase every single time it wants to climb it, the physical hardware is going to destroy itself pretty quickly. Vision provides both longevity and efficiency.
The issue, though, is that adding vision has historically been really flawed. The traditional approach is called decoupled vision, where the robot's camera builds an explicit, complex 3D map of the terrain and then feeds that map to the controller. The problem? Well, maps are inherently noisy. If your map is even slightly wrong, your robot fails. The Stanford lecture highlights a massive improvement here called direct integration. Instead of building a flawed map, the AI feeds egocentric depth data from the camera directly into the robot's brain using recurrent neural networks, or RNNs. This direct connection is so powerful, it allowed a tiny robot, one with very short legs, to completely adapt its gait, literally stepping highly sideways just to successfully climb giant, uneven stairs designed for humans.
Section 5. Grasping the physical world. Let's take the next logical step and see how all this builds from simple locomotion, just moving around, to something much, much harder. Extremely complex, dexterous manipulation.
Hand manipulation is where the physical world gets truly wild. Using the exact same principles we just discussed, researchers trained a robotic hand in simulation to rotate objects, and then deployed it blindly in the real world. The sheer madness of the variables this AI handles zero shot is just staggering. It seamlessly rotates items ranging from 5 grams all the way to 200 grams. It manages extreme friction differences, adapting perfectly whether it's holding a slippery ice ball or a rough, fuzzy kiwi. It even handles deformable shapes it has absolutely never seen before, like a squishy orange peel. How? Again, by using its own joint history. If a robotic finger expects to close all the way but gets stopped early, the AI instantly deduces it has made contact, figuring out the object's shape and resistance purely through touch.
And to prove just how ridiculously robust this AI pathway actually is, let me share this incredible number from the lecture. 4x. Researchers took this exact same reinforcement learning structure we've been talking about and applied it to a flying drone. The result? The drone successfully adapted and flew even when it was swapped for a physical body that was 4 times heavier than the simulation expected. They literally shot the drone out of the air with a tennis ball striking its propellers, and that rapid adaptation module instantly adjusted the motor velocities to just keep it airborne. No big deal.
Section 6. Exceeding human capabilities. As we reach the final destination of this AI pathway, we have to look at the ultimate form factor, the absolute holy grail of robotics, general-purpose humanoids.
We've seen that AI can make quadruped robots walk brilliantly, but making a humanoid manipulate the world is a whole different ballgame. You might wonder, why is manipulation so much harder than walking? Well, because walking is mostly rigid body physics. But if you want a general-purpose humanoid to chop vegetables or knead dough in your kitchen, you suddenly have to simulate incredibly complex, deformable objects. And remember our recipe for RL success from earlier? Well-specified rewards. How do you mathematically specify the exact reward for correctly kneading dough or the precise perfect thickness of a sliced vegetable? Endlessly handcrafting these varied, highly subjective reward rules is currently the massive bottleneck holding back general-purpose humanoids.
But there is a guiding light here, anchored in a really famous piece of philosophy in the AI space called The Bitter Lesson by Rich Sutton. He writes, "General methods that leverage compute are ultimately the most effective and by a large margin. So instead of painstakingly handcrafting explicit robot rules for every single chore, the winning bet will always be to improve our simulation technology so we can just throw massive computing power at it. Scaling compute and simulation will almost always defeat trying to manually engineer human intelligence into the machine."
Which leaves us with this mind-bending final thought for today's explainer. Currently, the robotics field is mostly striving for human parity. Just trying to get a robot to do the dishes as well as we can. But remember, AlphaGo didn't just match human Go players. It invented completely alien moves that no human had ever seen in thousands of years of play. As we scale up these simulations and reinforcement learning, will the physical robots of tomorrow discover biomechanical solutions, movements, and efficiencies that are completely alien and frankly superior to our own. It is an absolutely incredible future to look forward to. Thanks so much for joining me on AI Tech Pathways, and keep your eyes on the physical world because AI is officially stepping into it.